All right, in this video we are going to work on calculating the rate of change of quadratic functions. So first off, you can see the definition of rate of change is just a rate at which one quantity changes in relation to another quantity. You may also know this as slope. Rate of change and slope, basically the same thing here. Even though we're not talking about linear functions so much, we're still going to find it in the same way. So the rate of change formula is the same thing as the slope formula. We're going to find the difference in the y coordinates and divide that by the difference in x coordinates of two ordered pairs that are on our function. Normally this is really easy because normally we've just got a line and we pick the xy coordinates from one point and we pick the xy coordinates from a second point and plug them into this formula and we've got our answer. It's pretty similar with quadratic functions. The only difference is the quadratic function, of course, it's a parabola, which means we don't have the same rate of change or the same slope throughout this graph. So for instance, if we took these 2 points right here, we would still use the rate of change formula, but we would get a negative slope, right? Since the function is decreasing on this interval. However, we could pick two completely different points. We could pick this point right here near the vertex and this point towards the top. And here, we're going to get a completely different rate of change or completely different slope, whatever you want to call it. So we're still using the same formula, but just know your rate of change is going to be different depending on the two ordered pairs that you've chosen. So let's look at one example where they give us an equation. So we've got a skyrocket is shot into the air off of a 2-foot platform. Its altitude, ht in feet after t seconds, is modeled by the following equation. I always like to draw a little picture. It doesn't have to be a work of art, as you can see there. But that's kind of an idea of what we're looking at. We're looking at an upside down U-shaped parabola graph there. So the first question says determine the rate of change in the height of the object from 1 to 3 seconds. So normally we're used to equations given in terms of x and y. But this one uses h and t. So x is often referred to as the independent variable, and that's what we've got here, the time from 1 to 3 seconds. So they give us the t variable, and we need to come up with the corresponding height at 1 second. And they also give us another time of 3 seconds, and we need to find the corresponding height at 3 seconds. So this is a simple substitution into the equation. So at 1 second, I got 114. So the rocket is 114 feet in the air after 1 second. And then we're going to do the same thing by plugging in 3 in for t. And for this one, I'm getting 242 feet. So the first thing I recognize is this should be a positive rate of change because the skyrocket is increasing in height from 1 to 3 seconds. But now to actually find the rate of change, we're just going to use the y2 minus y1 formula, or in this case, the h2 minus h1 formula. 242 minus 114 divided by 3 minus 1. So I'm getting 64, so this means the rocket is increasing at 64 feet per second just on that interval. I would encourage you to try letter B. I'll put the answer up here in just a couple seconds. So I'm getting 194 and 258, which means, again, this should be a positive rate of change. So this time I'm getting a rate of change of 32 feet per second. So this tells me it is slowing down. We're probably getting pretty close to the peak before it starts dropping, which means from 6 to 9 seconds is probably going to be a negative answer. So try that last one, pause the video, and I'll show you the answer here in just a couple of seconds. So I got 194 and negative 142 here. The negative 142 doesn't really make a whole lot of sense in the real world application of this problem, because the rocket can't be negative feet high, but we're still going to go and calculate the rate of change, and if nothing else, this will give us an answer for a generic rate of change problem. So I mainly wanted us to see that sometimes the rate of change can be negative, even though this is not the perfect example. You kind of get the idea of how rate of change works when you have a negative value. All right, so an equation tends to be a little harder because you have that extra step. Sometimes they give you a table. So in this scenario, we have a rock that's dropped from a hot air balloon at a height of 100 meters. The rock's height from the ground in meters is modeled by the following formula, and they give you a table. So I've got my little picture there. They say dropped, but this is a quadratic. So there should either be a little bit of a curve to what he drops, or you could even say, oh, he actually throws it in the air and then it drops. But either way, that's kind of the picture that we're looking at right here. And then we want the average rate of change of the height from first 0.5 to 1 second. And the good thing is they tell us the exact height of the rock at 0.5 seconds in this problem is 98.8 feet high. And they tell us the height of the rock at 1 second is 95.1. So we have our ordered pairs right there. We don't really have to do any math to get the answer. All we have to do is set up the formula, y2 minus y1 divided by x2 minus x1. You can reverse the x and y coordinates. You'll get the same answer as long as you're consistent about which ordered pair comes first. So this should end up giving us negative 7.4 feet per second. Again, that makes sense because we started at 98 feet and we're ending at 95. So there's a negative rate of change. Encourage you to try B and then try C. All right, and I'm getting negative 12.27 feet per second. Try the last one. It's a little bit of a challenge. And then I'll show you what I got. So this last one, I'm getting negative 29.4 feet per second. Tricky thing is, this point was not in the table. So you had to go back to the problem and notice that they do also give you the equation in this problem. And use this equation to get the 21.6, so you can use the rate of change formula.